In this lesson, we're going to learn about functions. In order to talk about functions, we first need to talk about something called a relation. A relation is a very simple concept. A relation is just a set of ordered pairs. Any set of ordered pairs can be defined as a relation. When you have an ordered pair, you have two components to each ordered pair. The first component, typically we think of that as the x coordinate, and the second component we typically think of as the y coordinate if we're talking about ordered pairs or points in the xy plane. Well, in a relation, that first coordinate we call the domain. Okay? And again, that's typically the x coordinate. And the second coordinate we call the range. Again, typically that could be the y coordinate. So looking at this example right here, this set S is the three ordered pairs, 1, 3, -5, 4, 7, 3. Is this a relation? Well, yes, it's a set of ordered pairs. Any set of ordered pairs is a relation. Okay, so since it's a relation, what is the domain and the range for this relation? Well, the domain is the set of all the x coordinates, or the first coordinates. So 1, -5, and 7. If I was to write that down, I could simply say the domain is the set that contains 1, -5, and 7. It's that simple. And then what's the range? Well, the range is the set of all the second coordinates, and that would be 3, 4, and 3 again. Now, if I was to write that down and say, okay, we have this range, it's the set that contains 3, 4, and then 3 again. But since I already wrote 3, there's no need to repeat it. 3 is already in the set, so I wouldn't write it twice. So the range is the values 3 and 4. And that's it. Relation is a fairly simple concept. Okay, there's not much to it, so we can't spend a lot of time talking about it. But we need to talk about it in order to talk about what we want to do is deal with a function. So a function, okay? Let me use the highlighter, function, okay? A function is a type of relation, but it has a little bit more criteria to it. So in a relation, you have ordered pairs. You basically have first and second coordinate or first and second set, okay? Here's the first set. Here's the second set. We'll call that first set A and that second set B, which we know is the domain and the range, okay? But there's a way that these sets are matched together to make it a function. It assigns each element in the first set, A, to exactly one element in the second set, set B. So key words here. Each element in set A is matched to exactly one element in set B. And again, just like a relation, that first set is the domain. We call those the inputs, okay? And that second set B is the range, or we call those the outputs, okay? And there are reasons why we use those terms input, output. We'll talk about that later. So let's look at this general picture. We have one set here, that's set A. That's going to be our domain. We have another set here, B. That's going to be our range, okay? Each one of these circles contains a bunch of different elements, so there's a bunch of different values that are just made up here. I don't have to give them specific names, but these dots just represent the different values in the first set, and this represents the different values in the second set, okay? So, let's make this easy for right now, right? So if we match them up, that this element is matched to that element, this element is matched to that element, this one is matched to this one, and this one is matched to this one, okay? Then this would follow the definition that we just laid out for a function. Each element in the first set, A, is matched to exactly one element in set B. This one goes to 1, this one goes to 1, this one goes to 1, this one goes to 1. And so that type of mapping or matching is what would define a function. Well, let me give you another example. Here's one set, say A. Here's another set, B. And let's say I had, I don't know, these three values here, and I had these values here, and I matched them this way, such that this matches to this matches to this matches to this, and this matches to this. Would this matching define a function? The answer would be no. The reason being is right here. This element in set A is not matched to exactly one element in set B. It actually is matched to two different elements in set B. So it goes against this simple idea here of exactly one. Therefore, this is not a function. Okay? What if, I give you one more example, and let's say set A, set B, 1, 2, 3, 1, 2. This gets matched to here. This gets matched to here, and that's it. This is set A, this is set B. Would that be a function? The answer would be no again, but not because this one is going here and this one is going to that same value. Technically, that follows the definition. Each element here is getting matched to 1. This one's getting matched to 1. They happen to be matched to the same one, but they're matched to exactly 1. So technically, it still follows the definition. The problem here is this one right here not getting matched anywhere. It has to get matched to exactly 1. So it would have to go, say, to there maybe. If that happened, okay, then we have a function. If not, this is not a function. Well, this is a pretty easy fix. We could just say, well, let's take this element out of our domain. All right, now we have a function. The fact that this element over here doesn't have anything matched to it is not actually a big deal. It still follows the definition of a function. So hopefully this gives you a better idea of what that definition is stating. Now, we're not going to do this particularly this way, okay? We're going to look at equations and determine whether or not that equation satisfies this idea of each element in the domain, the first set, is getting a match to exactly one element in the range, the second set. Just look at these characteristics we talked about with functions that are important. Each element in the first set A must be matched with exactly one element in set B. And if it's not matched with an element, then it doesn't end up being a function. Some elements in B don't have to be matched with anything. Totally fine. Two or more elements in A can be matched to the same element in B. Totally fine. An element in A, which remember is the domain, cannot be matched to two different elements in B. I should say two or more elements in B. Okay? So these were the examples that I was just giving of things that were either happening or not that were making us follow the definition of a function or not. So to further talk about these different elements, the first set and the second set element, we did call the first set the domain set, okay? Again, typically these would be x values. These are called the independent variable values, okay? And then those variables that are representing the range values, which again typically are y, but it doesn't have to be, but typically y, we call that the dependent variable. So first set variable, independent, second set variable, dependent variable. And if we're working with an equation with two variables, let's say x and y, okay, y is considered to be a function of x if it can be uniquely solved for x, which basically means if you can take the equation, get y by itself, therefore solving it for x, okay, then we can say, based off of this information, whether or not the equation represents a function. So first, let's look at these three different tables and determine if any of them define a function. So let's look at the first one. We have an input of 2 matched to 1, an input of 5 gets matched to an output of 3, and an input of 8 gets matched to an output of 6. Does each one of these elements get matched to exactly one of these elements? Yes. So therefore, that would define a function. Let's look at the next one. -3 gets matched to 5, 0 gets matched to 1, 4 gets matched to 5. Now, this gets matched to 5. This one also gets matched to that same value. It has the exact same output, but that is okay. You can have two different elements in the domain get matched to the same element in the range. Totally fine. That's still a function. Let's look at the last one. 1 gets matched to 0, 5 gets matched to 2, but then 5 also gets matched to 4. That right there, not a function. You have this element as your input, 5, that's getting matched to two different outputs. That can't happen. So that table would not be a function. So let's look at a couple of equations and determine whether or not we have a function. So first, this equation. Could we determine whether or not this equation represents y as a function of x? And when you see this wording, it's extremely important. Y as a function of x, meaning y came from x. So x was the starting input and y was the output. Okay? That means y came from x. Y was a function of x. Okay? So the way we can determine that is to simply solve these equations for y in terms of x. So if we were to get y by itself here, that would be very simple. Subtract this 2x squared to the other side, subtract the 1 to the other side, we get minus 2x squared minus 1. And we would say, okay, well, for each x that we were to plug in here, would it give us one y output? Well, think about it. If you were to plug some value in here for x, what would you do? You would first square it. And when you squared it, you would get a single value out of that operation. Then that single value would be multiplied by -2, thus still giving you a single value for this whole thing. Then that single value from there would then in turn have a -1 subtracted from it, thus still giving you a single value. So a single x would give you a single y. Now, because this is a square, you would have two different x's giving you the same y, but that's okay. If I plugged in -2 or I plugged in 2 for x, they would give me the exact same output. In this case, it would be -2 or 2 squared being 4. Then 4 times -2 is -8. Then -8 and a -1 would give me -9. But again, that's okay. Two different x's giving me the same y is fine, but I can't have one x giving me two y's, but that can't happen with this operation, so yes, this is a function. So then the question always comes up, well, shouldn't that happen for every operation? Well, not necessarily. Let's look at this next example. If we were to solve this equation for y, we would have to get rid of this square. Well, you learned in algebra, in order to do that, you need a square root. If I took the square root of both sides of this equation, that would get rid of the square. However, when you do that, you need to do the positive and negative square root. And that right there is the issue. If I were to plug a single value in here for x, let's say I plugged in 4. If I plugged 4 in for x, then y would equal plus or minus the square root of 4, which would be plus and minus 2. which those are two different values, positive 2 and negative 2. So you're saying this one x value now got two y values. That can't happen. So this is not representative of y as a function of x. Okay? So hopefully that gives you a better understanding of how to look at an equation and determine whether or not that equation represents y as a function of x. Since certain equations would represent a function and others would not represent a function, we want to use a specific notation for the ones that do represent functions so that we know right away that we're looking at a function. And so typically what we want to do is name the function. And we can name the function anything we want, okay? And this is important if we're working with multiple functions at one time. F tends to be what we use to name a function, but it's completely arbitrary, but F obviously for function. And since we're going to solve these equations for y in order to determine if we do have a function, and y is a function of x, what we do is we replace the y with this notation f parentheses x, which is read f of x. And since y is a function of x, that should make sense to replace y with this f of x notation. So in that previous example, I could have wrote that equation as f of x equals negative 2x squared minus 1 instead of y equals negative 2x squared minus 1. It's the same equation, but now by using this notation, I know right away by looking at it, I'm looking at a function. F, again, would be the name of the function, and this variable inside the parentheses represents the independent variable or the domain variable for the function. So common letters we use to name the function f, we say f of x, we could say g of x, we could say h of x. Changing the letter out in front just changes the name of the function. If we're working with multiples, the letter inside represents the variable of the function. Typically it would be x, but it doesn't have to be. We could see a function when we say f of t, in which case now t is the variable of the function. And we would go, I don't know, f of t equals 3t plus 1, okay? But now you see t is the variable for the function. These variables are completely arbitrary letters. X is the domain, y is the range. They don't have to be those letters, but those are the ones we're most commonly using. But we can change it to whatever we want, and as long as we know what variable is the independent variable, then we know what variable to work with in this function. And then we know what function we're working with by the name we gave it. So this is a very convenient way of representing functions, but again, typically we'll use x and y will be represented by this f of x. So you could take the y out and put this f of x in its place. Once we have these functions notated in such a way that we have f of x equals, we can then talk about evaluating these functions. And what I'm saying is figuring out if we put something into the function, what would come out of it. And so this idea of this example saying f of x equals x squared minus 4x, find f of 2, which basically is saying if 2 was in our domain, where would it go? What would it get matched up to? What would the output be? What would the range value be for this domain value? So the idea here is that's saying that 2 is your x, right? 2 is your x value. Well, this function tells you exactly what to do with that x. I should square it and minus 4 times that value, basically plugging the 2 in where the x was. And that's very simple to do. You would have 4 minus 8. 4 minus 8 is negative 4, so there's your output. So if I plug 2 into the function as my domain, the range value would be 4. If I said, find f of 4a, well, it's the same thing. It doesn't matter what your input is as long as it goes to exactly one value. So if I said find f of 4a, I should do the same thing that I did with 2. So square it, 4a squared minus 4 times that value. In which case 4a squared is 16a squared. Then negative 4 times 4a is negative 16a. If I could simplify it, I would, but I can't. If you want to say factoring it is simplifying, you could do that, but I don't want to say that factoring is simplifying. So in this case, that would be what f of 4a gets matched up to. So again, 4a goes into the function, and 16a squared minus 16a comes out. Again, if I said find f of x minus 1, x minus 2, okay? Same exact thing. Don't change it. The function is what it is, and whether we're plugging in 2 or 4a or anything, we should do the same thing. Square it minus 4 times that value. And just knowing your algebra, if you square x minus 2, you get x squared minus 4x plus 4. And then if you distribute this negative 4 in here, you get negative 4x plus 8. And therefore, if we simplify this one, which we can, this negative 4x and this negative 4x combine to give me negative 8x. This 4 and this 8 combine to give me 12. Then there would be my output. So x minus 2 gets matched to x squared minus 8x plus 8 plus 12. So no matter what you plug into the function tells you what to do with it. So that's a pretty simple concept we should be able to evaluate. Here we're going to look at a unique type of function called a piecewise function. And a piecewise function comes in all shapes and sizes. In this case, this piecewise function f of x is defined by two different functions, x squared plus 1 and x minus 1. Now, one thing that happens with a piecewise function is that you have to specify what values of the domain will be used for each piece. So x has to be less than 0 to be able to use the x squared plus 1 piece. And it has to be greater than or equal to 0 for the x minus 1 piece. Notice there's no overlap between which x's will go where. That's important because we have to follow the definition of a function of 1x gives you 1y. If 1x can go in both pieces at the same time, then you would have two different f of x values for that. So this piecewise function is defined by the two separate functions, and each function has its own values of the domain that are associated with it. So if I wanted to find, say, f of negative 1, I have to know what piece I would use for that particular x value. So in this case, x is less than 0 because it's negative 1, so we should use this piece, x squared plus 1. So I would have to square the negative 1 and add 1, which would give me 1 plus 1, which is 2. What if I want to find f of 0? Well, f of 0 would use this piece, because this piece says when x is greater than or equal to 0, and we certainly are equal to 0, we should define it by using that piece. So we have to take x and subtract 1, so 0 minus 1 is negative 1. And then finally, f of positive 1, again, greater than or equal to 0, use this piece, 1 minus 1 gives me 0. So piecewise functions can come in all shapes and sizes. There's no limit to the number of pieces you would have. As long as you know what x values are going to go to which piece, you can work with that function just as well as any other.